Okay, today we have problem 5-51 out of the Shigley textbook, and this is a problem that builds upon problem 380, which has been solved in a previous series of videos, and we're asked to build upon that solution to determine the minimum factor of safety for yielding of this shaft using both the maximum shear stress theory and the distortion energy theory. So if you haven't seen that video, then all you really need to know to solve this problem is that in that problem we analyzed the stresses in this shaft. We worked out where the location of maximum bending moment is, and then we worked out where the location of maximum tensile stress due to bending is, and that was at point C here, so near this this bearing here, and we worked out the maximum shear stress and the maximum principal stresses, which I've just pasted here, and these values excuse me, are all that we're going to need to solve this problem 551. So for the first part of this problem, it asks us to determine minimum factor of safety using the maximum shear stress theory. So let's start with that one. And the maximum shear stress theory says that our safety factor is equal to our yield strength divided by the 2 times our maximum shear stress, which is also equal to the yield strength, excuse me, divided by sigma 1 minus sigma 3. And you can prove to yourself that these two equations here and here are the same thing using Moore's circle if that doesn't look right to you at first glance. But in any case, we are going to need the yield strength and the maximum shear stress, or the yield strength and the first and third principal stresses. So let's solve it both ways. But first, we're going to need the yield strength. And to get this, we need to go to table A-20. And this problem tells us that the material is 1018 cold drawn steel. So if we go to table A-20 and we look for the SAE number 1018, and we look for the cold drawn properties, then the table will tell us that the yield strength of that material is 370 megapascals. Okay, so that's the first part of what we need to plug into these equations. Now let's just directly use the shear stress that we have from solving problem 380, and then we're going to be pretty much done here. So if I plug in my yield stress, that's 370 megapascals, and divide by 2 times the maximum shear stress, which was 144 megapascals, then plug that into my calculator, and I get a safety factor of 1.28. Okay, now let's try it using the second form of this equation written here, just to see how that would work. So from our previous problem, we have that sigma 1 is equal to 276 megapascals, and sigma 2 is negative 12 megapascals. Now, these have been a little bit mislabeled because for any stress state, we're going to have sigma 1, which should be greater than or equal to sigma 2, which should be greater than or equal to sigma 3. So we're always going to order our principal stresses from most positive to most negative. And so if we have a stress state with two principal stresses, that means that our third principal stress must be 0, because we're looking at a state of plane stress here. So if I order my principal stresses, I would have sigma 1 is 276 megapascals, which is greater than or equal to 0. So my second principal stress should be 0, greater than or equal to negative 12 megapascals. So keep that in mind anytime you're looking at a state of plane stress, that there is a third dimension, and we're assuming that the stress in that third dimension is 0. So depending on what the magnitudes are and the signs are of your other two principal stresses, that third principal stress may be sigma 1, it may be sigma 2, it may be sigma 3. But here it's sigma 2, and so if I now plug that in to this form of the maximum shear stress theory, then I'm going to find that 370 megapascals divided by 276 minus negative 12 megapascals is going to also be equal to about 1.28. Okay, so that's the maximum shear stress theory. And now the problem asks us to also find the safety factor using the distortion energy theory, which I just abbreviate as DE. And to do that, we're going to need the equation for this distortion energy theory, which tells us that our safety factor is equal to the yield strength divided by sigma prime, where this sigma prime, remember, is our von Mises stress, and there's a couple different forms of that equation. But this yield strength is going to be exactly the same as the yield strength that we used for the maximum shear stress theory. That doesn't change. And our sigma prime equation, I'm going to use the form that has principal stresses, since that's what we have. So it's sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 1 minus sigma 3 squared. All of that divided by 2 and take the square root. So again, we need to make sure that our principal stresses are ordered in this way so that we have sigma 1 is the most positive and sigma 3 is the most negative principal stress. So when I plug those values into my equation for the von Mises stress, I get that it's 276 megapascals squared plus sigma 2 is 0, sigma 3 is negative 12, so we end up with a positive 12 megapascals squared. It's going to be squared anyway, so it doesn't really matter. And then we get 276 minus negative 12, so that turns out to be a plus megapascals squared. Okay, and again, all divided by 2 and under the square root. So let me calculate that really quick. We've got 276 squared plus 12 squared plus 276 plus 12 squared. All right, and then all of that divided by 2. and take the square root. Okay, so I got 282 megapascals for my von Mises stress. And then to work out our safety factor, all we have to do is plug that into our equation using our yield strength of 370 megapascals. So 370 divided by 282 is our safety factor, and that is 1.32. And so you can see also that our safety factor using the distortion energy theory got a little bit higher than our safety factor using the maximum shear stress theory, and that is to be expected, right? We talked about in class that the maximum shear stress theory is more conservative than the distortion energy theory, although the distortion energy theory tends to be more accurate. So depending on your application, you will need to use your engineering judgment to pick which one of these theories should be used. And that's all for this video. So thanks for watching. See you in class.